Hello everyone, welcome to the course on digital signal processing. This is lecture number 5 and in this lecture we will see the discrete Fourier transform DFT. So before starting with the DFT, we must have a brief idea about the Fourier series, continuous time Fourier series. Afterwards we have the continuous time Fourier transform. So I'll be starting with the continuous time Fourier transform. So what we observe here is that we have the signal, a continuous as well as aperiodic signal in the time domain, and what we are already aware that the continuous time Fourier transform for this type of rectangular signal is nothing but a Singh function. So we'll be having a Singh function. So if you'll see the behavior here, we can see the signal is continuous and aperiodic. Also in the frequency domain, we can say that the signal is also continuous as well as aperiodic. Now what happens if we'll do the sampling? If the sampling is performed in time domain, so the signal will become discrete. The continuous signal will be now a discrete sequence or the discrete signal, and what we can say here, the signal is discrete as well as aperiodic because the nature remains same. Here if the signal was aperiodic, here also the signal is aperiodic. So the sampling in one domain basically results in the periodicity in the another domain. So what we can say that the signal here will become periodic, means this entire waveform will repeat itself after a period. We'll talk later on what is the period over here. So this is nothing but called as a discrete time Fourier transform, DTFT. So DTFT basically convert a discrete aperiodic sequence into continuous periodic, where the period of this the signal is nothing but 2 pi. So this we are already aware that what is the relationship between the continuous time Fourier transform and the discrete time Fourier transform. Now if we talk about what is discrete Fourier transform, so if we perform the sampling in the frequency domain, so what I can observe that sampling in one domain, sampling in the frequency domain results in the periodicity in the another domain. Means what happened, the time domain signal will now be the periodic version of the above signal. So we'll be having the sequence, and again this will be repeated after, let's say, the time period. Later on we'll see what is the time period for this discrete, and for this is also discrete periodic. So that means the discrete Fourier transform converts a discrete periodic sequence into discrete periodic, whereas this is in time domain and this is in frequency domain. So this is called as discrete Fourier transform. So next is if we talk about that the discrete Fourier transform computes the value of Z transform. Later on we'll see what is the relationship between the discrete Fourier transform and Z transform. So DFT computes the value of Z transform for evenly spaced point around the unit circle. We are already aware in the Z domain what we have a complex Z plane. So this point number 1 will going to be explained later on with the help of some mathematical derivation. So the Z transform for evenly spaced point around the unit circle for a given sequence. If the sequence is to be represented is of finite duration, that is, it is having some finite number of non-zero points or non-zero values. So the transform we are using is called as discrete Fourier transform, DFT. So DFT is having n number of applications, starting with the linear filtering, correlation analysis, and the spectrum analysis. These are some typical applications of discrete Fourier transform. Now we'll talk about the mathematical equations corresponding to discrete Fourier transform. So we have two equations. One is called as analysis equation, one is called as synthesis equation. So this is called as analysis equation. whereas this is called a synthesis equation. So the first equation, if you can clearly see that x of k is a DFT of a sequence which is xn. So the equation is x of k equals to summation is n equal to 0 to n minus 1. Means here this xn is nothing but periodic with a period of capital N. So xk equal to summation n equal to 0 to n minus 1 x of n e raised to power minus j 2 pi nk divided by capital N, where capital N is the number of points or the length of the input sequence xn. So this equation number 1 basically gives you the discrete Fourier transform of xn, the periodic sequence. Whereas if we talk about the inverse discrete Fourier transform ITFT, so I'll be having x of n equals to 1 by n summation. Now instead of xn, we'll be having capital X of k. So k equal to 0 to n minus 1 xk e raised to power j 2 pi nk divided by capital N. We are already aware that in most of the analysis equation we are having a negative power, whereas in most of the synthesis equation we are having a positive e raised to power plus j. So where n equals to 0 to n minus 1, where n is the length of the input sequence or n is the length of xk, the discrete Fourier transform. So now we'll talk about the relationship. What is the relationship between the discrete Fourier transform and the Z transform? As we are already aware that CTFT is a special case of Laplace transform, because CTFT basically evaluates on the j omega axis. So in a similar fashion, we just want to derive some relationship between the discrete Fourier transform and Z transform. So we'll start with Z transform first. We are already aware that x of z is nothing but summation n equals to minus infinite to infinite x of n z raised to power minus n. Where I'm talking about that the ROC includes the unit circle. We are already aware that what this indicates is, it indicates nothing but that our sequence xn, this means xn is stable, or its Z transform exists only when xn is stable. So we are putting on condition that ROC includes the unit circle. Now, if xz is sampled at, we can say, n equally spaced point on the unit circle, this is, let's say, mod z equals to 1, a unit circle, and it will make some n's. It will sample this at n equally spaced points on the unit circle. So what I can observe is, I can replace z by e raised to power j 2 pi k by capital N, where k equals to 0, 1, 2, and n minus 1. So I'm having, so what I can say that x of k means x of k is the discrete Fourier transform, is nothing but it's equal to Z transform when Z is nothing but when xz is sampled at n equally spaced point on the unit circle. Means this is equal, xk equals to xz with this particular condition. So this equals to summation n equals to minus infinite to infinite x of n e raised to power j 2 pi nk divided by n. Means whatever we have, we just put the value of z in our first equation. Let's say I'll be having this equation of x of k. Now this is not over yet. So this is identical, the last equation is identical to the Fourier transform x e raised to power j omega. This is called as a discrete time Fourier transform, DTFT. So DTFT, we are already aware when we have the sequence which is discrete as well as aperiodic in time domain. So this is identical to the discrete Fourier transform, discrete time Fourier transform evaluated at n equal space frequencies, where we can say omega k is nothing but 2 pi k by capital N, where k varying from 0 to n minus 1. So if the sequence xn has a finite duration, is having a finite duration of length n, because we are already aware that in DTFT the sequence is of infinite duration. So if we have xn is a finite duration of length n, then the z transform can be given as, we can have the finite points where n equal to 0 to capital N minus 1. Rather, in the previous stage, what we have minus infinite to infinite, right? But if we have some finite points, so definitely the summation will going to be changed from 0 to n minus 1. Now, by substituting the IDFT, the equation number 2, what we have in our last slide, we just want to replace in this equation, let's say equation number 2. So, x of z equals to summation n equal to 0 to capital N minus 1. And instead of x of n, I can write down the equation for IDFT and z is to minus n as it is. Now, I'm going to change the order of the summation. This will go outside and this n equal to 0 to n minus capital N minus 1 goes inside and z is to minus n goes inside. So, we'll be having like this. Now, if you clearly see that this is a summation and this is a finite, I can make a finite GP over here. Finite summation हम यहाँ पे use कर सकते हैं. And what I can write? We can write that 1 by n summation k equal to 0 to n minus 1 xk as it is, and 1 minus z is to power minus n divided by the whole factor what we have. And if we'll further simplify this, because this term is independent of k, I can take outside and like this. Let's say this is equation number 3. Now this above equation, this is nothing but, if we'll see that this is equal to what? X of z. This is nothing but x of z. And x of k is nothing but DFT, discrete Fourier transform. So the above equation is identical to that of the frequency sampling form. So when this is evaluated over a unit circle, so what I can put is, instead of z, I can put z equals to e raised to power j omega. So wherever we have z, I can put e raised to power j omega. So I'll be having one more relationship, which is x e raised to power j omega, the whole factor as it is, instead of z here and here. So this was the relationship between the discrete Fourier transform and Z transform. Also, we can say in our last slide that this was a relationship between the discrete Fourier transform and DTFT. This is nothing but DTFT. And this is nothing but DFT. So this was equation number 4. Equation number 3 gives you the relationship between the discrete Fourier transform and Z transform. So after these relationships, we just want to take some numerical. So derive the DTFT of the sample data sequence xn, which is a finite duration, having let's say total number of samples are, let's say, 6. 1, 1, 2, 2, 3, 3, and compute the corresponding amplitude and the phase spectrum. We are already aware that if we are going to calculate the discrete Fourier transform, that is in frequency domain, so we are interested in talking about the magnitude response and the phase response, which is also called as amplitude and phase spectrum. So I will start with the basic formula, what we are aware to calculate the discrete Fourier transform, which is x of k equals to summation n equal to 0 to capital N minus 1 x of n e raised to power minus j 2 pi nk divided by capital N. Now we are already aware that k can take values from 0 to n minus 1, and if n equal to 6, the length of input sequence, so the k will be from 0 to 5. So if we put k equal to 0 in our equation, so I'll be having nothing but the summation of all the samples, all the points. So n equal to 0 to 5, this is nothing but summation of xn. So we are going to add the sample points. So it will give you 3 plus 3 plus 2 plus 2 and again 1 plus 1. So this value is nothing but equals to 12. So this x of 0 generally is very easy to calculate. It is nothing but the addition of all the points. Now when x equals to when k equal to 1, it will be a bit complicated because we'll be having some exponentials involved now. So x of 1 equals to, again we have summation 0 to 5, and instead of k, I'm going to put k equal to 1. So it will further simplify this and expand for different values of small n, starting with 0, 1, 2, 3, 4 and 5. So the simplified x of 1 we can observe is a complex quantity, which is minus 1.5 plus j 2.598. So in a similar fashion, we can calculate x of 2, we can calculate x of 3 and x of 4, and similarly we can calculate x of 5. So we can write down that this is x of k generalized form. So the samples x of 0, x of 1, x of 2, x of 3, x of 4 and last x of 5. That is the discrete Fourier transform for the input sequence xn. Now, so this is x of k. Now, as per this particular numerical, we need to calculate, we need to plot, or we need to observe the magnitude and the phase spectrum. So if I can clearly calculate the magnitude of x of k, it can be quite easy. The magnitude of 12, we are already aware, it is 12. Now a plus jb under root of a square plus b square. Similarly, I can calculate the magnitude of all x of 0, x of 1, x of 2, which is something like this. Now the corresponding phase spectrum x of k tan inverse of 0, we are already aware that nothing but it is 0. Tan inverse of 2.598 divided by minus 1.5. So we can easily calculate with the help of calculator also. It comes out to be minus pi by 3, minus pi by 6, 0, pi by 6 and pi by 3. So this is nothing but the phase spectrum, and the above, this is called as a magnitude spectrum, or it is called as amplitude spectrum of xk. Now we'll talk about one important theorem which is going to be used in discrete Fourier transform, which is called as convolution theorem. So as we are already aware, the convolution, we have studied in the signal system also, that we have the linear convolution. So linear convolution means if we have Hn, the LTI system, the impulse response of LTI system Hn, and if Xn is the input, so I can calculate the output of the system with the help of a tool which is called as convolution, x of n convolution with h of n. So this is called as a linear convolution. So convolution is, this is called as a linear convolution. We can say that the convolution in one domain is nothing but the multiplication in the another domain. So x of n convolution with h of n is nothing but x of k, capital X of k, multiplied by capital H of k. So now when we have the periodic sequences, then a new convolution come into the picture, which is called as circular convolution. So here we can see the sign over here that we have a circular convolution with a circle over here. X of n circular convolution with h of n is nothing but the DFT will be the product of the discrete Fourier transform of individual x of k multiplied by h of k. Now this is called, the symbol is called as nothing but the circular convolution. So we just represented this circular convolution in the form of summation, discrete summation, where this mod is called as, this is nothing but the modular operation. So since both the signals, whether it is xn, whether it is hn, both are of the length of n points. This is called as n point circular convolution also. Means both the sequence xn and hn has to be of equal length, and the length is nothing but n. We are already aware about the linear convolution, this convolution summation we are having. So circular convolution is also commutative, exactly like our linear convolution. This is nothing but the property, we can say, property of the circular convolution. So we have some differences between the linear convolution and the circular convolution. Complexity wise, definitely it is less. Linear convolution is less complex. Here we have circular convolution. It is bit complex because here the convolution summation is nothing but based on modulo operation. Here the shifting is linear shifting, whereas we can say we'll be seeing in the circular convolution that the shifting of the points will be nothing but in a circular fashion. The number of samples in linear convolution, we are already aware that if xn is of length n1, hn is of length n2, so the entire length of the output sequence will be n1 plus n2 minus 1. Whereas we can observe in circular convolution that the length will be maximum of n1 comma n2. Now, basically the linear convolution is used when we are a bit interested in calculating the response of the system. Now here circular convolution, we have some other approaches also. Matrix convolution approach we have. In MATLAB, during the simulation we are using the MATLAB tool. So we have a tool which is called as we have a function, built function CONVA comma B. It will give you the convolution, but that convolution is nothing but a linear convolution. Whereas if you are writing CCONV, so CCONV means C means circular convolution of A comma B. So these are some small differences between the linear convolution as well as circular convolution. So if the sequences are periodic, definitely circular convolution is used. When the sequence is aperiodic, generally we say that we have the linear convolution. So we are starting with the first approach, which is called as the graphical approach or the graphical method. So this graphical method, how I can compute the convolution, circular convolution of x1 and x2. So if we have x1, I can write down in a anti-clockwise manner. x1, 0, x of 1, x of 2, x of 3 and x of 4. Now x2 of n, again in a similar fashion. Before we proceed with the circular convolution, let us see this one, x of m and h of n minus m. Or you can clearly see this is x1, this is x2. So x1 of m, and here I'll be having x2 of n minus m. So basically I need to make minus of m. How can I make minus m? I can just take the mirror image if they are going in anti-clockwise. So the minus will be somewhat in a clockwise manner. This is called as a folded sequence. And initially I'll be interested in calculating x1 of m and x2 of n minus m, where n is nothing but 0, let's say. So x1 of m multiplied by x2 of minus m. So both the sequences will be overlapped, and accordingly we'll just perform the convolution operation, which is nothing but the product as well as summation. So the first point we can calculate like this. Product will be, we can take the product 1 multiplied by 1, again 1 multiplied by 1, 0 multiplied by minus 1, 1 multiplied by minus 1, and similarly 0 multiplied by 0. So if we can solve this, we are having the output, which is x3 of 0 is nothing but 3. Now what is next is I'm going to calculate x1 of 1, x2 of, or I can say this is m, 1 minus m. So in a similar fashion, I can just rotate this in a anti-clockwise manner by a single point. So after the 2 minus n, I can just again shift by one more in an anti-clockwise manner and just perform the product and the addition, the summation. This is called as the convolution summation. So for the last numerical, I can just compute the circular convolution also. So we have one other method which is called as a matrix multiplication method. So this matrix multiplication method, again we have some standard kind of approach how I can write down like this. So this is a small, we can say a short trick you can say to calculate the circular convolution like this. So finally what we have some numerical generalized linear convolution. We are already aware the method, we have already seen circular convolution. So circular convolution, we have the method. You can use a matrix approach also. You can use a circular convolution, that graphical approach also. And finally, the third approach, which is called as GFT and IDFT. Means first we need to make the number of samples equal. We just perform the we just compute the DFT. We just perform the product, and we just perform the inverse discrete Fourier transform. So it is a bit lengthy task. So this is the final result over here. So again, these are some key points. We find the resulting sequence obtained by both linear convolution and the circular convolution having different value and different length. Linear convolution results in an aperiodic, I have already discussed, whereas circular convolution results in a periodic sequence. Circular convolution will produce the same sequence values as those produced by the linear convolution if we perform the padding of 0. So these are the three key points which we have used in the circular convolution. These are the references. Thank you.